Ms. Manar Ahmed Fouad Abdul Latif. I work as a lecturer in Alexandria University, Egypt. Currently, I'm a researcher in the Università degli Studi di Milano, University of Milan in Italy. I hope you can see my screen.
Yeah, we can see your screen.
Okay, perfect. So today I'm gonna tell you a story about carbon monoxide, how we return this invisible killer gas into a friend through the palladium-catalyzed reductive cyclization reaction. Just a historical view about our group, that our group is specialized in the one-step reaction to indoles. In 1986, Chinini group presented the first reductive cyclization reaction to get indoles. But unfortunately, these kind of reactions were running in the presence of pressurized carbon monoxide at very high temperature. So harsh reaction conditions was required for this kind of reaction. Of course, in the presence of highly safety measurements and using the autoclave. Today, and after more than 3 decades, our group, which is the former Chinini group, actually Ragheni group, presented the reductive cyclization reaction, but using alkyl or aryl formate esters as in situ carbon monoxide releasers. In that case, we don't need any more to the pressurized carbon monoxide. We don't need any more to the autoclaves, and actually mild reaction conditions could be used in this kind of reactions. Our group strategy actually based on 4 main ideas. The first idea is the using of glass pressure tube, which is a glass equipment, could be easily accessible to all the synthetic chemists over the world. The second thing is the use of formate esters as alkyl or aryl formate to be employed as efficient carbon monoxide surrogates, which they are cheap and low toxic. And it's worth to mention that during and at the end of the reaction, the amount of the carbon monoxide remaining inside the reaction is always small and very easy to just get rid of it. The third idea is to use milder reaction conditions. So to run the reaction at low temperature and even low catalyst loading. In some cases, mixed solvent system is allowed to get some heterocycles whose synthesis had previously failed in some past experiments. Last but not least is to convert these kind of reaction, the reductive cyclization reaction, into a general tool. So all the chemists around the world can use these kind of reactions. This is just to show you some application of this reaction that was previously published. We synthesized oxazines. We synthesized also indole through the cyclization of orthonitrostyrenes. And recently we published our last paper through the cyclization of 2 nitrobiphenyls to get the carbazole, which is very hard compounds to get in normal conditions and need several steps to get your carbazole. Anyway, if you need any information about these publications, you can easily scan the QR code and easily you will find the world of the phenyl formate as a carbon monoxide surrogate. Today, I want just to speak about synthesis of indoles. Since we are already finished the cyclization of orthonitrostyrene using phenyl formate as a carbon monoxide surrogate, and this work actually is all done. In Germany, they said 2 heads better than 1 head. So we need another alternative or another pathway to get indoles to make the life easier and easier and easier for the chemist. So the cyclization of beta-nitrostyrene had been performed in the same strategy. We don't need pressurized carbon monoxide. We don't need autoclave. So we start from previously published preliminary test from our group. We used the same strategy. We started from beta-methyl beta-nitrostyrene, palladium catalyst in presence of phenanthrolene as a ligand, and we get the indole in 41% yield. So starting from this experiment, our work was permitted. and we started our optimization of the reaction conditions. As you see here in the table, we had tried many and several solvents, several bases and several base amount, and we got a lot of numbers to explain. As you see here from the first look, we have in some cases, of course, good conversion, but not always good selectivity. And let me drag your attention into two specific experiments. In the first one, we didn't use phenyl formate, we didn't add base. So basically this reaction was running in the absence, in the complete absence of the carbon monoxide. The second reaction was in absence of phenyl formate, so there is no carbon monoxide indeed, but also there is a base, triethylamine. Let me use my laser pointer. Okay, so we have triethylamine here, and we got 61% of conversion. These two experiments means that there is actually a decomposition for the starting material. But unfortunately, no decomposition product had been observed, except for very small amounts of benzaldehyde, suggesting that they are oligomeric or polymeric species could be formed starting from our substrate in presence of triethylamine. So at the end, we said, okay, probably there is a competition between the cyclization reaction and the decomposition reaction. And from this result, apparently the decomposition reaction had won this round. But we are not quitter. We tried to perform some another experiments with this regard. Then we said, okay, maybe increasing the amount of the catalyst could do something in the reaction. Also, we had studied the effect of the solvent. We got almost, in case of acetonitrile and DMF, the same result, but at least we had used acetonitrile as a solvent, since it's much more cheaper and it's much more easy to remove it from the reaction. Also, it's less toxic. So we tried also to run the reaction at higher catalyst loading. So we used 5 mol% instead of 1 mol%, but actually increasing the amount of the catalyst, as you see from the number, from the conversion and the selectivity, the increasing the amount of the catalyst didn't solve the problem at all. Okay, so what about the amount of phenyl formate, which means to increase the pressure of carbon monoxide inside the reaction? Actually, from previous literature and from our previous publications, this kind of substrate, the beta-nitrostyrene, needs high carbon monoxide pressure to react. So we can use actually much more phenyl formate, 350 microliters of phenyl formate, and we got actually better selectivity, not the best, but of course it's better than the 40%. We got 47. But using this amount of phenyl formate make us far away from our main target, which is to just get rid of the using of autoclave and make this reaction general tool. So we cannot use glass pressure tube simply with this amount of phenyl formate. So our group suggests to never work with this amount, because actually it's the maximum level of carbon monoxide pressure that can glass pressure tube handle. So working with such a large amount of phenyl formate is unsafe. But anyway, we got the best result in the presence of these kind of compounds. We are not quitter, as I told you, so we started to shift the optimization from beta-methyl beta-nitrostyrene to use alpha-phenyl beta-nitrostyrene instead, which they are much more stable, and we can optimize them much more easy than the other one. We started with the temperature, and as you see, we tried like 5 temperatures starting from 110 to 150, and the best one, as you can see, is 140. After that, a drastic decreasing the selectivity had been observed. Then we tried also to optimize the amount of base, and the best thing we have observed is 120 microliter, and you can see that there is linear increasing between the selectivity and the amount of the base. But we didn't want to actually to increase the amount of the base any further because we were afraid from the decomposition reaction that we had observed previously in case of beta-methyl beta-nitrostyrene. So we decided to use 120, now no more than that. Okay. For the catalyst loading, actually, we tried to do the reaction in presence of half mole percent, 1-2 mole percent. And even in case of half mole percent, we had increased the time from 3 hours to 6 hours, and we got more or less the same result. In case of 2 mole percent, we decreased the time, and it's the same result. And it's worth to mention that in case of 2 mole percent, we actually observed the reaction completion after 1 hour of the starting. So that means increasing the catalyst loading is just increasing the rate of the reaction, but not really affecting the result. So 1 mole percent actually is the best one to start this reaction. Also, we had blade with phenolphthalein, with the amount of the ligand had been used, and you can see that 5 mole percent give us the best result among all the 2.5 mole percent or even 10 mole percent. Finally, we have to also check the amount of phenyl formate. We use this 200, 260, 350. As I told you, despite that 350 is not really safe to use, but we said, okay, we have to compare between these conditions and this substrate and the other one. So in case of even 350, you may say, okay, you have to increase the amount of the base because maybe it's a little bit obvious, but I have to announce that triethylamine is pretty crucial in the reaction because actually it dissociates the phenyl formate to give us at the end the carbon monoxide. So the amount of triethylamine is not only important for the reductive cyclization, but it's also important for the dissociation and releasing of carbon monoxide. So we used, in that case, we used 200 microliter of triethylamine, and as you say, the results is more or less the same. So at the end, we decided to stay with, to stick with our conditions, as you see here in the slides. And that was the good time to proceed for the substrate scope. We had prepared some substrates to pursue the reductive cyclization, as you see. And this is the time for our strategy to interfere with these substrates and to get them, boys. And the substrate scope, as you see here in the next slide, with the yields in front, just under the compounds. Okay, just to quick reminder with the optimized condition, we have always used 0.54 millimole of beta-nitrostyrenes, the substrates, 260 microliter of phenyl formate, 120 microliter of triethylamine, and the total volume of the acetonitrile used was 10 milliliter. As you see here from the substrate scope, the reaction tolerates with both electron donating groups and also electron withdrawing groups. Also, it had to be mentioned that the reaction is compatible and tolerated with this substrate, which is contain a phenyl ring in the alpha position and methyl group in the beta position, and give us actually moderate yield, which can be optimized in the future. Okay, for the reaction mechanism or our catalytic cycle, actually it's from our previously publication, we can see that phenyl formate in presence of the base, which is help in the dissociation, release the carbon monoxide and the phenol as the side product. Carbon monoxide start to react with the palladium catalyst or the palladium complex, which is actually in situ formed using palladium bisacetonitrile dichloride plus phenolphthalein to give us the true active catalyst, which is easily can be activate the nitro compound through the electron transferring to give the radical anion and radical cation. This radical anion in presence of carbon monoxide, and through the successive accumulation of these anions in the reaction solution, the nitroso species could be easily formed. In the presence of palladium catalyst, some studies also said that we don't need really the palladium catalyst here, just accelerating the process, but it's easily to be cyclized to give the N-hydroxy-indoles, which is easily deoxygenate to give us our final product, our desired indole, and regenerate our active catalyst to interfere again with the catalytic cycle until all the nitro group has been finished. Then we can observe at the end of the reaction palladium 0 or palladium black species had been precipitated, so we know that the reaction is already done. At the conclusion, we can say that our beta-nitrostyrene react easily in the presence of 1 mole% of our palladium catalyst, and our carbon monoxide system phenyl formate in presence of triethylamine 5 mole% of the ligand, and in milder temperature or milder conditions comparing to previous reactions of the same kind, to give us our indoles in yields up to 92%. At the end, if you need, of course, more information, you can find this work published recently in Catalysts. You can scan the QR code to get the publication easily in your mobile phone. And at the end, I'd like to thank you all for your kind attention, and to thank also my group for the working. We were actually helping each other. Professor Fabio Ragaini, Dr. Francesco Ferretti from University of Milan, Dr. Mohammed Al-Atawi from Alexandria University, and Dr. Dario Fermenti from Rostock, LICAT, Dr. Dua Ramadan from Alexandria University, and of course to thank you all for your kind attention. And please, if you have any question, you can use my email or the chat, or even ask me now if you want. I can't wait to hear your thought. Thank you very much.